Okay, first of all, thanks to the organizers, especially to Stefano Galatolo, who invited me to talk in this occasion. Okay, and unfortunately, I will talk some old work that I have done, and indeed I am here in Pisa this time just to try to continue this kind of work. I'll tell you the subject in a minute. Okay, my interest indeed is just to understand the behavior of vector fields presenting a singularity or an equilibrium point from the topological point of view and also from the statistical point of view. Okay, there are significant examples of such flows. Is the famous Lorentz flow and the geometric Lorentz flow, and the Lorentz-like or singular hyperbolic flows. Indeed, this model here, this is what is called nowadays the geometric Lorentz flow that models the original equations by Lorentz, and that was Lorentz gave that equations in the 60s just to model the long-term evolution of climate. And at that time, it was impossible to solve the equations, which were quite simple. And this model was presented by Guggenheim, Holmes, Guggenheim and Williams in the 60s or 70s, in the beginning of the 70s, just to give an answer to the Lorentz conjecture that was that that equations would present an attractor with zero volume and with initial dependency on the data. That meaning is that once you start with two nearby points, and when you evolve through the time, the orbit will be separated. And this model was given by Guggenheim and Williams, and indeed it proves the conjecture by Lorentz. This is the model of Lorentz, a tractor that has the famous butterfly shape, and Lorentz did this with a computer, in the old computer in the 50s, I think, last century, and then it was quite interesting. And here is the singularity is sitting here, and the orbitals go around the singularity with this shape completely handily. You cannot prevent where they are. Some like this. Okay, and from the statistical point of view, properties are often a better object to be studied than the pointwise behavior. The future behavior of initial data can be unpredictable, but statistical properties are often regular and their description can be simpler. And with Galatolo, indeed, we related the heating time with the local dimension of the unique physical measure of a geometric Lorentz flow. And we established a log law for the heating time that gives a quantitative indicator of chaos. Indeed, I don't know what is going on. Okay, the heating time, you know that you pick a point and you fix a target. You fix the first time that the orbit hits this target. And okay, what we proved is that the chaotic system, indeed, it is expected that the orbit of a point must visit a target with a frequency mu of the target, mu for small, that is, it is expected that the behavior is like this, no? It's proportional to 1 over the measure of the target. In general, this is not the case, even for a nice set of balls, as balls. Okay, and then if we denote the local dimension by d mu x0, a point there, we have that the local dimension is the limit when the radius of the target goes to 0 of this quantity here, okay? And for systems with superpolynomial decay, it was proved that this limit here, or the heating time, is just the local dimension of the point, okay? And what the main theorem for flows, that was with Galatulo, we proved that for geometric Lorentz flow, for mu almost every point, we have that the heating time behaves is like that, the local dimension minus 1. And later we extended the same log law, holds for a Lorentz-like flow in the sense that, okay, you have this model, the geometric Lorentz flow, the characteristic is that it presents a unique singularity, which is quite well behaved, and it is attached to regular orbits of the system, and this behavior is robust. Lorentz-like flow means that, okay, then you get free from the number of singularities. You can have more than one singularity, and you have some other expression or a condition on the behavior of the flow that guarantees that the behavior is more or less like the Lorentz, the geometric Lorentz flow. And okay, we proved this with Victor Araújo, and this kind of result indicates the chaoticity of a Lorentz-like flow. And then just the proof of this result is, they depends strongly on the first return map. That you see that if you have a geometric Lorentz flow, you have a cross-section, a unique global cross-section, and you can define the first return to this cross-section. And then this map is called the first return map, or Poincaré map as well. And all that proves depends on you have the flow, and then you cut one dimension and goes to a two-dimensional problem. The flow is on the space, three-dimensional space, and then through the cross-section, you cut one dimension and go to a two-dimensional analysis with this map, which is discrete somehow. And for this map, you have to prove that the first return map has exponential decay of correlations. This means that, okay, that you have this constant here, and this, the return is independent, you know? You have, this is the formula for decay of correlation. And so we were able to prove this. And the question that arises is why we can prove this kind of equation or exponential decay of correlation for the first return map in dimension 2, or discretize the Lorentz flow, and why we cannot prove the same result for the flow. That's why the motivation indeed for this talk that I'm doing now. And why this? The point is that what happens near the singularity. The singularity or the equilibrium or is like this. You have a fixed point or where the flow is zero. And if you take the linear part, you have three real eigenvalues. One, they are all distinct, two are attracting, and the one expansion, and you have this relation. You see that you have one direction that contracts stronger than the other one, just one which is expanding, and the behavior nearby is like this. You take a point, and then it goes in this direction like a saddle, okay? And you still have some, if you sum this eigenvalue here with this one, you have that the sum is bigger than one. There is one relation between the eigenvalues of the linear part of the flow here at the singularity. This is the problem, and then you have what you can do. You see that you can prove that if you have a flow that the singularity is like this, in the sense, Lorentz-like, in the sense that you have the eigenvalues are just like this. And then you can prove that this line here, that is the line you have the flow in this direction, it's not contained in the attractor in some sense, okay? So you can just eliminate this, and eliminating this, which is called the strong stable manifold, you forget this, the effect of the strong stable direction, and because it does not interfere in the dynamics. And what you see is this kind you take. You take, here is the unstable direction, this is the weak stable direction. You take an interval here, transverse, and another one here. If you pick 2 points there, you start flowing, and then you have this shearing here. Because once you get near the singularity, you see that the time is growing. Each time that, if the point, do not see in the here, this point, or if you take it near, it's go quite slowly, and then it's different. You have, at the same time, you have this kind of displacement or shearing, okay? That is the main problem and why you cannot prove immediately from the one-dimensional or two-dimensional map associated to a geometric Lorentz flow that the decay optical relation or mixing relations, whatever, directly from the discretized map. Okay, this is a problem. Okay, so we start thinking, this is because what we call shearing effect, and then after these identifications, in the sense that, okay, you cross this strong stable manifold, you have to, we were looking for some map that could model this behavior. And then after some identifications, we just take, I'll pass through here. You can see that this changed the name of variables and doing some identifications. You can see that this map here, this is defined, okay, here. This is like a skew product. In the first coordinate, you have the double mapping, and on the second coordinate, you have the translation by this kind of map here. C is a constant, and x minus a half to the power half. And this you can just put modulo 1, and then you get this map in the torus, okay? And this can be seen as a simplified case of the shearing effect for flows presenting an equilibrium attached to regular orbits. Okay? Okay, and then this is the map that we arrived at, and our goal was to prove that this map has exponential decay of correlations. Okay, so just next we describe the results we have proved for this. Usually they call also a cross cosine instead of the product. Okay. So remarks is that needed for alpha bigger than 0, we have that this here is equal 0 for x equal to half, and then you have a line of singularities where the map is not defined when you look in the tori. You can look at the map here. You see that for x equal to a half, this is not defined. No? Okay, and so moreover, define 0, 1 times 0, 1 with the torus, the skew product is defined, and the circle x equal to a half is a curve of singularities. Okay? We remark that, okay, this, let's assume that the alpha is equal to 1, but it's not. The point is that indeed the circle x equal to 1 is a line or a circle of singularities that you have when you are analyzing this map. What is the dynamics of this map? You see that the successive iterates by f of a rectangle R are transformed in a numerator set of strips accumulated to this circle x equal to 1 in the torus. You see that because this line here is sitting in the base, in the first coordinate, is just the double, and go, and this is replacing everywhere because the first coordinate is a double map and
Somebody is moving the microphone and drowning out the. Okay, they start. Thank you.
Okay, and then since the first coordinate is the double map, 2x, the double map, it's Bernoulli in the basis, and then it's dense in the base, in the 0, 1, and like that, like this. This is just we are the effect of the iterating the map f in a rectangle. Okay. This effect together with the fact that the pre-orb by this map here, which is the double map of the circumstance in the torus, are responsible for the breach dynamics of F, indeed. Okay. And since the length of the vertical segments are preserved under F, the action of F on the vertical borders of the rectangle is just a translation depending continually on the point in the basis. And go on to the pre-orbit. Basic properties are that, okay, this map is not expanding. It's not expanding because any map that you take there, the derivative is just 0, 1. It's not expands. For all P in the torus, there is no stable manifold. And for any iterated, such that the image, the pre-image is like this, the image is like this, is defined on an unstable manifold. And the derivative admits no non-trivial dominated splitting. And if this constant is rational, there are infinitely many periodic points. And if this constant is not a rational number, there are no periodic points. And the map preserves the Lebesgue. Conclusion, standard techniques in dynamics using the existence of stable and unstable manifolds are usually useless to get any result here. Okay. And, we have a formula. I think that I will skip the formula, but I'll be back here. Okay. You can obtain, I have to tell you a little bit. Okay. Why I will talk about the formula with that? Because all the results we have done, I would say, in a primitive way, in the sense that we use the properties, how you say, na mano? We didn't use any strong technology to prove our results. We just use the formula, how you get the points in we wrote the points in base 2, and then calculated the pre-orbital, which were the formula of the pre-orbital, and many calculations to arrive to these equations or formula. And okay, this is like using the double map behaves as a shift map, no? Left shift map, and using this we were able to give a formula to the pre-orbit of any point, and we use this later. And this is just the graphic of the pre-orbit when you look just in one of the coordinates. This is not so. I'll not give this. There is a general formula that the iterate you can write like this. The enésimo, if you take 2 points, x and y, you have a formula like that you can get inductively, and where the second coordinate is like that. Okay, and you have to write the points in basis 2. Anyhow, okay, I'll not talk about this. And then the first result. The first result that we proved at that time was that topological mixing. Well, recall that a map is topological mixing if for all pair of sets A and B in the manifold, we have that there is an integer such that the pre-image, any pre-image of A intercepts B for any bigger or equal this number. And we prove that for C bigger than 0 and the alpha bigger than +1, I think that, yeah. I think that there are something wrong here, but we prove that the cycle, the co-cycle is topological mixing. And the second result is mixing Lebesgue in the sense that, okay, you see that a map is mixing for a measure if there is, for a pair of sets in the manifold, you have that the limit of the measure of the pre-images of A intersecting B is like the product of the measure of the sets. And we have proved that for alpha equals to 1 and C bigger than 1/4, this skew product or cocycle is just preserves the Lebesgue measure in the torus and in mixing with respect to Lebesgue. Okay, and we also have proved that the height of return points. This is the point that in the beginning we thought that we had proved the decay of correlations, but unfortunately we didn't. We didn't just because we start with two rectangles, and then we can prove that the height of the points that return to a rectangle is exponentially decay exponentially. But the constant here depends on the rectangle that you take. Okay, that was, and indeed, right now, what I would like is to improve this result here. We are talking with Stefano and Roberto and Marmi, whatever. I would like to talk to anyone which is, how you say, would like to discuss this kind of point, just to solve that map has exponential decay of correlations. And indeed, nowadays, there are, I insisted that all we had proven, that was proved with José Vietes and Roberto Marcarian, both from University of Montevideo in Uruguay. And everything that we have done here was really, I don't know how to express myself in very primitive, I would say. I don't know. Because we didn't use, nowadays we have very strong technologies to study this point of view. For instance, to study the transfer operator, and usually there are this method from using the transfer operator, and it's a very powerful technical, and which were used by Liverani and the co-authors to prove decay of correlations. But we still didn't arrive to this, and then I would like to continue and to see if we can really prove. No, I will not. The proof goes just, as I said, we profit from the fact that the base map is Bernoulli, and so successive image of a rectangle accumulates everywhere, like this. It's a small rectangle, you just do like that. And the images of Fn for alpha equal to, for these values, and the successive n is like that. This is the graphic of the second n coordinate that indicates that you really have mixing. But no, I'll not prove this. This is the graphic of F in R2. And and the base, just one comment to prove that mixing Lebesgue, a basic lemma is to see that given an epsilon, small epsilon positive, there is an integer such that for n bigger or equal to n, every horizontal arc with length delta x and pre-image, this is the formula for the, you see that I am written this a number in the basis 2. It results is that the length of the pre-image of this arc is bigger than this number here. Okay, all this is okay. We're done, and I think that is, I'll stop here because it's not, my point is that I would like to prove that indeed this map here has exponential decay of correlation. That is what we are trying to do during this stay here now in Pisa. Thank you. Okay.
Thank you, Zeze. Any questions? If you can, there is a question from Angelo.
You speak about the transfer operator, okay, of this map. You were able to compute analytically the transfer operator, or you do numerical work on transfer operator to, for instance, calculate well polyglot resonance that are connected to the Gaio correlation?
I'm not an expert on this. I'm not. I'm talking with Roberto, and then Roberto was talking about to apply this, and it's also Stefano. And there is a formula for this kind of mapping and the transfer, but unfortunately, the techniques that usually Liverani and the co-authors and even Roberto Castorini that is here with co-authors, they used to prove the decay of correlation does not apply here because you don't have the conditions. I think that I had another, do I have time or not? I don't know. Just to tell you that I had another idea. I was, because you see that there is one point when you want to prove that something has decay or whatever. There are two approaches. There is one approach that uses the Liverani's transfer operators. There is another approach that is manually, in the sense that, okay, it's like this comes from Boeing, all right, that you have three conditions. You have one condition is that expansiveness, or you have expansiveness. And the other one is you have specification. Specification means that is something that replaces the Boeing balls or whatever, and that controls how near you stay along time orbits, and continuity, some kind of continuity of the observables, okay? And then using this approach, maybe we can go through this. But you know that this map is not expensive. Then it's another obstruction. And I had one idea, maybe we could codify, introduce some notion to give expansiveness to this map. Which one? You know that, remember that picture that I put with the rectangles? You see that the vertical sizes, they don't increase, they just translate. They just translate one to the other one, okay? And then you could just split the torus in the direction of the basis there, and then say, okay, I'll give a notion of expansiveness that codify. One point is above and the other one is below this line, and maybe you can distinguish orbits through this new notion of expansiveness. I don't know, I just had talking with people, I don't know, maybe, I don't know. Okay, that's it.